Okay, so the name of today's lesson is Properties of Logarithms, but before we do that, I want to remind you what the properties of exponents are, because you'll remember an exponential and a logarithm are inverse functions, so their properties are going to behave very much like inverses as well. So let's remind ourselves how exponents work, and that is when you have the same base, x, you can have an exponent times the same base with a b exponent, and what do? You add the exponents. Okay? And we also know that when you have a x to the a divided by x to the b, as long as the bases are the same, then I can take that base and simply subtract the exponents. And when I have an exponent raised to another exponent, then I just have x to the a n. Okay? So I have these properties of exponents, and I very much want to think about this while I'm doing properties of logarithms. So it would be nice to have them showing, but I write too large, so you're pretty good though, you remember those well. So let's talk about properties of logarithms. What if I had two logarithms? No, sorry, rewind. What if I had one logarithm? And it has a base, but inside there is a product of a times b. Okay? What I can do is I can actually expand that into two logarithms, both with that same base, because remember, bases always have to agree, plus a second logarithm with just one of the factors. Okay? So I'm separating the factors with its own logarithm. So this one logarithm is now the sum of two logarithms. So this product here is a sum, okay, in the logarithms. Okay. And let's just go through the next property. So you have these all because they're all related. If I had a divided by b, rather than adding the logarithms, what do you think we're going to do? Pretty straightforward. We'll simply turn that division into subtraction. And just make sure you have the order correct, that, you know, the a is on top, so it has to be the positive one, b is on the bottom, so it has the negative. And that works out too if you think about what does a negative exponent mean. So, and plus, put together with this next property, let's say you had an exponent raised to a power, okay? Then what happens is it becomes multiplication. Remember how when it was an exponent, we multiply the two exponents together? But now you take that and you multiply x times the logarithm. Okay, so this one in particular is so enormously powerful for us, okay? I mean, it's done an amazing thing for us because it's removed an exponent. We don't have an exponent anymore in this expression because now it's kind of down on the same line. There's no exponents. It makes so many things easier, okay? Solving equations becomes easier, taking derivatives and integrals and everything just becomes easier when you don't have that exponent, okay? So taking a logarithm is often very helpful. Alright, I want to make sure that you've written these rules down on a piece of paper so you can keep referring back to them for all these next examples we're about to do. Okay, for this example, I want to evaluate the log base 4 of 32. Now, we have other ways to do this, right? But I want to show you how to do this using the properties because it makes it's a very good way to highlight these properties. So what I'm going to do is, instead of calling it 32, I'm going to call it, got a couple choices here, let's call it 2 times 16. Okay, so I've just replaced 32. And then, now that I have this multiplication, these two factors inside the logarithm, I can write two separate logarithms as a sum. So that product, okay, there, inside turns into the sum of two different logarithms. Okay? But now I have this problem where, you know, the bases and the inside aren't matching up. So it's a little more difficult to take those logarithms. It's actually easier to start over here. Let's do this one. If the base is 4, then it's a good idea to write 16 as 4 squared. Okay? And if the base over here is 4, it's a good idea to write 2 as 4 to the 1/2 power. Because remember, 1/2 power is a square root. The square root of 4 is 2. So I'm rewriting 2 as 4 to the 1/2. I did that because my base is 4, so I want insides to be of 4. Alright. Now I'm going to use that rule with the exponents, right? And that means whatever I have as an exponent, okay, can come down in front as a multiplier. So what happens is that 1/2 comes down in the front, 1/2 log base 4 of 4 plus, this exponent comes down as a factor in the front, multiplies log base 4 of 4. Okay, so see how I've done this? I've brought the exponents down to the front with multiplication, so I don't have exponents anymore. So now it's really easy. I know log base 4 of 4. What is that? I can evaluate that very simply because I know that's 1. So this is going to be 1/2 times 1 plus 2 times 1. Everybody should be able to evaluate that logarithm. And what do I get? 1/2 plus 2 is equal to 5/2. So my answer would be 5/2. So maybe it's a bit long and involved, but it does show you all those great properties and how we use them. Okay, so we use these properties to evaluate more difficult logarithms. Maybe I already know some of the basic ones. I've gone to a lot of trouble to figure out some of these. Like I already figured out log base 4 of 2, this one here, is 1/2. I'd already figured that one out. I took some time, I figured out log base 4 of 3 was about 0.8. It's going to be less than 1, right? Because 4 to the what power is equal to 3. And I know 4 to the 1, that 1's too big, right? Because it would give me 4. So I know it has to be a little less than 1. So let's estimate to the best of our ability, what would the log base 4 of 5 be? 5's a little more than 4, so I know it has to be a little more than 1. 4 to the 1 point, maybe 2. Maybe not quite that much, but close. So I've made some good guesses there as far as some basic logarithms to work with, and from this information I'm going to evaluate. Let's try, I have to put these together somehow. How about the log base 4 of 30? Okay, and think about that using the logs that we have. I could let you do it if you want, but I'm going to go ahead and do it as well. I'm going to call the 30. How am I going to break that 30 down? Using multiplication, division, powers, da-da-da-da-da. Let's see, if I called it log base 4, I can use a 2, a 3, and a 5 to get me that. Oh, well, it's obviously 3 times 10, which is 3 times 2 times 5. And this is the nice thing about these properties is they're scalable. You know, if it works for 2 factors, it works the same way for 3 factors. So we can do that actually, and now I've got log base 4 of 3 plus log base 4 of 2 plus log base 4 of 5. Because remember, multiplication in here, oh, that looks cute, doesn't it? Multiplication in there turns into sums of separate logarithms. Okay? Some people would call this expanding the logarithm. So I know what all those values are. Up here I have worked them out already. So I've got a 0.8 plus 0.5. Let's go ahead and do that. Plus 1.2. That's pretty easy to figure out. 2.5. So my estimate, and I have to say estimate, right? So I'm going to use an estimation symbol here and here, because once I left, you know, this above here, things were real exact. But after I started, you know, estimating and rounding and things like that, I have an approximation. So my approximate answer, 2.5. Okay, write those values down again that we had at the beginning, because we're going to use those for our next example and let you do it. And actually what I want you to try is evaluating log base 4 of 2/3. I'm going to pause it and see what you get. Okay, I got negative 0.3 because I broke that down into log base 4 of 2, then minus log base 4 of 3 because the 3 was the divisor, so he is negative. Put my values in, and again I should have used approximate symbols. Okay, those were all really good examples of when it's helpful to expand a logarithm. We had one logarithm, and it was more helpful to write them as sums of multiple logarithms, so it was expanding. We can talk about condensing, because those rules are kind of like if and only if statements. They go both ways, okay? And condensing is going to help us a lot when we solve some of these log equations. Now, don't forget the easy log equations that we've already done, but sometimes you'll see equations that are a little more complicated that have something like this. Let's try 2 logs, log base 2 of something, plus another log equal to something besides 0. 0 would have made it nice, would have been easy, but no, we have to have something else here. So it sure would be nice if I had just one log on the left, one log on the right, so that everything would cancel and would be good. What you don't want to do, let me stress this, you do not, because of this plus sign, you cannot cancel, cancel, cancel. That does not work. Okay? Let me take that back. Oh, it's not going to let me do that. That doesn't work. Can't do that. Okay. Because there is this plus sign right here, we're going to have to condense first and then use that property of logarithms that you want to use so badly. So let's condense these into a single logarithm. So log base 2 of 4x times 5. If I'm adding 2 logarithms, it means I have to multiply those 2 arguments together, is equal to log base 2 of 40. Working this out a little bit, I'm going to get log base 2 of 20x is equal to log base 2 of 40. Now I have one log on the left, one log on the right. Now I can go ahead and cancel those out so that I have 20x is equal to 40, and of course x is equal to 2. Okay, so here's where it really was imperative that we use the property to condense first and then solve. Okay, maybe in some of those other problems you might have been able to work it out a different way, but in this case, I gotcha. You got to use the properties. I want you to try one. I'm going to make it pretty hard. Log base 2 of n is equal to 1/3. So there's a number in the front. Okay, you're going to have to take care of that with a property. Log base 2 of 27. Plus, okay, so there's that sum of multiple logarithms, log base 2 of 36. Think about how you might proceed, but I think I'm going to go ahead and do this one with you because it brings up the point here. I cannot add these 2 logarithms together because one of them has a 1/3 on it, okay, and the other one doesn't. So I can't combine those yet, okay? So what we have to do is sort of remove the 1/3 from in the front, and we'll just take it up into the exponent, so it's up there instead. So what we're going to have is working the property backwards, log base 2 of 27 to the 1/3 power, okay? So this exponent raises up to the exponent, this factor in the front. And then I don't have to do anything to this guy. He's just sitting there waiting around to get combined with the other one. Now I could go ahead and combine, but I know what 27 to the 1/3 power is, so I'm going to go ahead and do that. Log base 2 of 3 plus log base 2 of 36. Okay, so now I have these 2 logarithms. Oh, I still have my left-hand side. He's just been hanging around. I want to go ahead and combine these 2 now, okay, because they have the same coefficient. I can combine them, so that's a single logarithm where I multiply together. Because they had started as the sum of 2 logs, I'm going to take it as 1 log and multiply 3 times 36 and get 108. So that's log base 2 of n. They're both log base 2. Here's where I get to cancel out the logs on both sides. So n is equal to 108. And I'm done. Okay? So making sure you had the same coefficients before you condense 2 logs. And you do that with that power. This sort of thing here is called a power rule, and that's the one that I like so much. Okay? Power rule. Okay, here's one more problem. I don't have a log on both sides. but I don't want to bring the log over to the right-hand side because then I'd have 1 minus that log, and that doesn't help me get to the point where I could cancel the logs either. So the only option left is to condense those two logs. So that's almost always going to be a good option here if you can do it. So I'm going to condense these two logs into one and then solve it the way I normally would solve a logarithm problem by using that definition, that if and only if statement. So go ahead, you try it, and I'll come back. I'm going to pause. Okay, for my solution I get z equal 1. It's pretty easy to condense the two logarithms into one logarithm. Then I use my if and only if statement here. Then I have to solve a quadratic. So I solved my quadratic. I made sure I had the equal 0. I factored it. I got two solutions for a quadratic like you expect. But I was on the alert. I was on the lookout, and I noticed that this z is equal to -10 does not work in the domain, right? I can't take the log of a negative number. So I wanted to be careful that that doesn't happen, so I have to cross out that solution. The only solution left is z equal 1. Alright, I think you guys are pretty good. We'll talk about decimals and a scale for measuring the loudness using decibels. Try and save our ears during those long concerts, loud concerts. We'll do it tomorrow.